Okay, so in my previous talk about a month or so ago, I talked about the some mysteries and controversies in fMRI, but I never got to challenges. And I realized as I prepared this talk, this could be a whole course, obviously, and so I had to sort of pick and choose what I wanted to highlight for the message, the essential message for each challenge. And this is not a comprehensive list either, but I like to, once again, I always like to put things into the format of like the three pillars or four pillars of what I think of as fMRI. So once again, challenges are not really controversies or mysteries. They could be, but they're rather directions that we want fMRI to go without a straightforward means to get there. I think that all the challenges that I'll present today are actually doable. We can, the field can achieve these, but it will take, and also I think that the innovations are all there for the most part, but it will take some sort of infrastructure changes and sort of high level sort of changes as well to actually get them implemented. And just to quickly kind of go over how I organize things. I'm organizing the challenges all sort of as a list, but I'd like to at least keep people thinking about the four pillars in this sense, that, fMRI sort of is developed along the lines of these interacting pillars, the pulse sequences, the paradigm designs and signal processing methodology, how deeply we can interpret the signal, how deeply we understand the signal. And then also, of course, these all feed into research and clinical applications. So, and then they all kind of feed off each other. And so that's kind of how things evolve. So as far as the challenges are concerned, I'm going to first list them all, and then I'll talk about each one, but then go into detail with a couple. So, and obviously some are incomplete, and of course, this is not a comprehensive list by any means, but, and some are near being achieved. So one challenge is seamless data code pooling and sharing, removal of all non-neuronal noise, spatial normalization of the bold signal weighting across variation across the brain, sort of a calibration, real-time assessment of, and all of these things are sort of there, obviously, but it's actually having it work all the time for everyone. Is my goal, is the goal of fMRI. Real-time assessment of ongoing state, fully understanding, in other words, resting state fMRI. Clinically useful biomarkers, I put that in quotes because it's sort of an overused term that sort of has a lot of meaning that is now becoming kind of a bad word. Practical clinical implementation, full individual subject characterization. So kind of being able to put people in the scanner and understand how they're similar and different to everyone else in detail as the brain function relates to their behavioral traits and states. Adaptive parcellation, possibly using global hyperalignment or things like that to account for some of the structural differences in the brain. Layer fMRI, whole brain directional connectivity and hierarchy to be able to achieve that information. Multimodal integration, sort of seamless integration of very complementary measures like EEG, optical imaging, structural, vascular, fMRI. Subcortical fMRI and connectivity is, I think, a close but looming challenge, which is really important to mental health. Robust subcortical connectivity assessment, that's sort of the same sort of thing, but this might be a little bit out of the range of realistic, but temporal spatial resolution of down to 10 millisecond TR and 0.1 millimeter voxel sizes, which is, that's the only one that I think that will take some sort of novel advances that I'm not aware of. More contrasts packed into the time series, more functional contrasts. I think that when we just collect with bold or vaso or whatever, I think we're we're missing opportunities to simultaneously collect more types of contrast so that we can do multivariate contrast assessment. Uniform shimming across the whole brain. This challenge should have been achieved decades ago, but it's still not. Migration of fMRI from something like cartography, where we're just describing where the brain areas are, to actually understanding mechanisms of brain function, which here we basically are looking at a very coarse spatial and temporal scale, but there's a lot of flexibility in terms of what we can do with our paradigms and how we can build our models to sort of fill that out potentially. We'll need other modalities. So starting with the, I'm not going to talk too much about data code and pooling and sharing, just because there's many efforts to do this, both in papers and in groups such as that directed by Russ Poldrak that has Open Neuro. And I think there's a general cultural shift that started maybe about 5 to 10 years ago, maybe even longer, towards pooling data. And also as scanning becomes more expensive, it's becoming much more common as well. And then code, I think with better communication, people are sharing that more. And I think that sort of has momentum. So the challenge of removing all neuronal noise. Oh, did I? Shoot. Okay. Oh, no. Okay, I'm gonna have to do that for every time. But anyway, so I talked about this a little bit in the previous talk, but so what actually is in spontaneous fluctuations? Well, of course, there's what we're interested in, the spontaneous neural activity, which also, though, involves shades of different types of neural activity. There's arousal, there's conscious thought, and there's unconscious processes that go on. Everything that's going on, for instance, a correlation between left and right motor cortex, that's not a conscious process. That's just happening. So I think that, probably the conscious thought is sort of related to the unconscious process in the sense that it's spontaneous. We don't control the spontaneity of it, but it feels like it's something we control because we have a thought and we're aware of it. It reaches our conscious brains. But I think that these two are linked. As far as respiration is concerned, respiration, there's mostly two types. One is sort of hard to get rid of, one is easy. Changes in B0, like for instance, if you breathe, especially in a high field scanner, you'll have a difference in susceptibility between your lungs and the outside air. And as you breathe in, your chest cavity changes. That will change that B field that will spill into the brain. But that's easy to get rid of because it's rhythmic. It's well understood. You just correlate against the bellows for the most part. Gets rid of most of it, but not all of it. But the hard one is subtle differences in your breathing depth change your end-tidal CO2, which is related to your blood PCO2, which modulates vasodilation. So the respiration effects that occur due to bold effects, that's harder to get rid of because you have to really trace carefully the bellows, and even still, you have to look at the subtle differences in the bellow depth to determine what the end-tidal CO2 is. And even still, there's regional variations. Katie Chang has talked about this as well. So, for years, people have tried just using regressors or something like retroiocor, and it never works really well, just because of the fact that the transfer function of how end-tidal CO2 changes and causes respiration-related flow changes is spatially variant as well, and it varies over time, and it's noisy. So it's really hard to get rid of. Thermal noise, motion, scatter, instability, these are more addressable. And pretty much all of these, and the goal of getting rid of all non-neural activity is that, one big goal is to say, well, if we look at the temporal, the image signal to noise versus the temporal signal to noise, our image signal to noises can be up to 1,000:1 ratio signal to noise, and we're still limited by a temporal signal to noise of 100:1. And if we can actually completely model out and understand this, we can actually potentially have a temporal signal to noise that matches our image signal to noise, which would profoundly increase the sensitivity of fMRI. But right now, pretty much half of this, at least half of, depending on your voxel size, half of the data are non-neuronal that we're still struggling to get rid of and model. And one idea is that, this is just basically a list of all the neural frequencies and that we care about that we might be able to see in fMRI. If we do a simple ICA, independent component analysis of the time series, we can get all these networks. But the problem with getting rid of the physiologic noise is that if you look at a power spectrum of the data, the physiologic noise components are highly overlapping with the resting state signal changes. So it's very in the power spectrum space, it's highly overlapping, which makes things very difficult. You don't want to throw the baby out with the bathwater in that regard. And so people also try to do spatial templates. Like, for instance, they know, like, if you have a motion, then your ICA component might look like edges. And people have tried to use spatial information to further filter this out. So just a nice reference article that's relatively recent by Cesar Galebro Gaudes and also Rick Reynolds here in the AFBI group, has a nice overview of all most methods for getting rid of noise. So, and like I said, right now, I mean, there's many different methods that use variations of ICA or whatnot to either, identify, these are all the networks identified from ICA. However, and then you could probably, eyeball the bad ones, but to make it automated is a little bit more tricky. So you actually have to have learning sets, and it's still not perfect. And also things that there might be a lot of real activation that looks like noise. So it's relying on this is probably somewhat of a dead end. Another technique that has been talked about, I think, in this course already is multi-echo fMRI, and that's where you collect at least 3 echoes. And this is a time series of activation. This is resting state. And the idea is that if it's a true bold effect, it shows a percent increase with longer echo time in a linear fashion. So here, basically 2 decay curves. This is the real bold. This column is bold. This column is artifact. And typically, when you take the difference of the decay curves, the exponential decay curves, you have a peak about the echo time equals to the T2 star. And the percent change keeps on going up linearly. But with artifactual signal changes, either S naught changes or other things, it's either something that just goes down or flat or random. So putting the data into ICA components and sorting them to the degree that they resemble percent signal change that increases with echo time, Prantik Kundu sort of developed a method for separating bold from artifact in this regard. So here are the ones, these are ICA components that show not a very good fit to this curve, whereas these components do. So it's a nice principled way that doesn't use the temporal features, it just uses the echo time dependence to get rid of the non-bold effects. Problem is that you also have still this respiration effect that's not necessarily neuronally related, and it's still there. So that's a hard, and there's other ways of getting rid of that as well that I won't go into in detail. But here's just an example. I kind of like to show this. This is just an example of a raw time series. It's where every image was subtracted from the mean. So you can't really see much in that raw time series. And if you're a raw bold time series, that's been where the bad components have been regressed out using multi-echo ICA, you start seeing just in the raw time series, the real neuronal, spontaneous neural activation. Problem is, you also see this global effect that comes in every once in a while too. So it shows both the kind of unique advantages and the global effect. And of course here, you just see this isolates all just the noise. All right, so the next one I'm going to talk about is spatial normalization of bold signal weighting across the brain. So this is a problem that sort of waxes and wanes in terms of its significance, in terms of what you're actually doing. So I'd like to show this, and I'm not going to go into this whole diagram, but this is all the neural information that we're potentially interested in. And this is how we chop up the brain, just in voxels. And the voxels contain various amounts of blood volume. And depending on the blood volume in the voxel, you'll have either a large bold signal or a small bold signal for a given oxygenation change. And that heavily weights things. I'll show a little bit more of that in a second. Different MR parameters, also modulate the signal magnitude. We've already talked a little bit about noise. And how do we actually deal with this? And as I mentioned, this signal can vary. It's a nice review article, or not really a total review article. It basically summarizes that when people say it's an indirect, bold is an indirect measure of neural activity, they're saying, well, not only is it a function of the baseline blood volume, venous blood volume in each voxel, but it also can be modulated by coupling. What is the coupling between the neural activity and the blood flow changes? So that's another variable that can vary, and that might vary from region to region as well. So of course you have differences in magnitude, differences in latency, and so on. And so all of these hemodynamic responses can vary over space. And if you're trying to interpret your signal, people usually say, in the past, distant past, they would look at the highest area of activation and say, oh, that's where the hotspot is. That's where the center of mass is. And that's almost certainly not true. That's usually where the big vessels are, near the center of mass of the area of activation, but never truly the center of mass. And just for fun, I figured I'd refer to an oldie but goodie paper. This is one of my papers from, I guess, 1997, which I showed basically these isocontour lines of the fractional blood volume. So how much blood is in each voxel versus the change in oxygenation versus the percent signal change. So these contour lines are percent signal changes. So typically, if you have a fractional blood volume of 10%, that's still a little bit high. A tiny change in oxygenation that would cause about a 2% signal change. But very quickly, if you get like half of your voxel filled up with a vessel, then for typical oxygenation changes, you would get up to 30 to 40% signal changes, which is huge, and which people see all the time. And one way of getting rid of that is calibration. This is just a sagittal cut finger movement in which I had a subject breathing 12% oxygen, which is less than the 21% room air. You can see all the big vessels just get dark. And then if they breathe 5% CO2, which causes global vasodilation, you see all the big vessels getting brighter than the areas, in the motor cortex. I mean, it's basically a blood volume. Both of these are blood volume maps. And, you can actually look at the percent change as a function of, as it relates to the percent change during finger movement. And you find that the areas that show the highest change during finger movement are also the voxels that show the highest change with each of the perturbations, the hypercapnia and the reduction in oxygenation. And if you simply divide the two, you can then say, well, these areas that show the highest ratio between those are the areas of true activation. So this is demonstrated in the map. So here's before the division, you have the hotspot in the sagittal sinus, and then after the division, the hotspots move to the motor cortex, or I guess this would be the supplementary motor cortex, because that was sort of like the precursor to a lot of different, more quantitative calibration techniques. And they're kind of important, and I think that people may do without really doing this, because if you calibrate, you're dividing, and that reduces the signal to noise. It's a pain giving someone CO2 before every single experiment, and so people are always looking for better ways of being more selective or having a more even distribution that's related to neural activity. One approach has been using like pulse sequences that are sensitive to blood volume, which it turns out is less sensitive to big vessel effects. But that's not perfect as well. So this problem has cropped up again in the context of ultra high resolution imaging. Uh, uh, it's especially problematic when you're trying to make a detailed interpretation of the signal change as a function of where it is in the cortex. And it turns out that with Peel vessels at the top of the cortex, that heavily weights the bold signal right here. So if you give hypercapnia, you have this heavily weighted towards the surface of the cortical layer of signal change. And then if you give activation, you have something like this. If you divide the two, like calibration is very similar to what I just showed, you might get a hump that looks like it's the real activation is in the middle. With vaso, you don't really have this problem as much. And so dividing it doesn't really do a lot, but you still have that. So calibration techniques are there. We're still looking for better ways of getting rid of the big vessel effects. So the next one I'm going to talk about is clinically useful biomarkers. The basic concept behind biomarkers is that the goal. I mean, this has been the goal of fMRI ever since this day one, where if you had a subject who might have undiagnosed schizophrenia, let's say, or something like that, then you put them in a scanner, you do a resting state scan. They have a signature pattern of activation or resting state pattern that's different than the normal population. And that's a biomarker. If it's robust, then you could say, oh, look at these images. We weren't sure, now we're sure this person has this, or it might recommend treatment, or it might recommend, what sort of treatment would be best for them. So that's the goal, to be able to put someone in the scanner and be able to say something about them that's clinically relevant that you can't get in other measures. And that goal so far has been completely unobtainable. And there's been a lot of false starts, and that's what has caused the field a little bit of controversy in the sense where people will claim, oh, well, look, we do 10 subjects, we see a difference between depressed patients and non-depressed patients. There you go. You just have to look for this pattern when you stick any other patient in. Problem is, it's never been fully replicable. Even if it looks like a robust pattern with 10 subjects, it turns out, in a large part because of this paper, which sort of really was a nice, line in the sand in the sense of saying, okay, this really is the situation. And the situation is that they were looking at populations of patients with psychosis versus without psychosis. And they found that to actually see any difference using resting state, where all the subjects are put into a normalized space, templates were created or parcellations were created. They looked at the time series. Significant correlations were found, and somewhat replicable findings were found only after about 2,000 subjects. And for everyone, there was like, oh my gosh, this is kind of an eye opener. And some people didn't believe it. Some people, like myself, feel like it's a well-done study, although there's a lot we can do to sort of push this back. And I believe that it's almost a straw man in the sense that they just looked at resting state, or no, they also looked at some other structural features as well. But also, the clinical populations were highly heterogeneous. So there might be very many different variations of people with psychosis that all have very different patterns that they all pool together. I personally think the biggest problem is that our brain structures are different enough that if you try to put our brains into normalized space and parcellate it, you'll get a lot of shifting of the parcel shapes and locations such that what you end up comparing after 2,000 subjects is barely anything in that regard. And so I think that reduces the power almost more than anything, but I could be wrong. That's just my own intuition. So the problem is that I'm doing this, but there's many other clinical applications that don't require biomarkers. And then the kind of the elephant in the room with this whole study is that, okay, maybe after 2,000 subjects, we can see something, But can we go back to a single subject now and be able to then say, we'll have enough signal to noise to say with certainty that they fall within one group or the other? Because that's another statistical problem that's much harder than just separating groups. So it's a problem. And I think as we better understand individual differences, we'll get our heads around this problem a little bit more. So I already talked about all this. We could have better tasks. We could have better normalization. We could have other measures. Even the paper they suggested multivariate approaches could be better as well. So I think there's many ways of bootstrapping this up that in which you might be able to get down to the order of hundreds, and then maybe looking at individual subjects. So the next one I want to talk about is okay. So let's say we do need biomarkers. How do we practically implement this? So that's the big problem. So right now there's a lot of clinical research, but not many people talk about actually using fMRI in the scanner, in a clinical scanner, in a way that a physician can just sort of, in the same way that they look at grayscale images now with MRI, they say, oh, there you go, there's a tumor, just like with this image. So practical clinical implementation, typically now with MRI, we have the right contrast weighting, and we either see a lesion or not, and that's it, we're done. Maybe we might add contrast agent or something to enhance it, but that's it. No processing, barely any processing. With fMRI, there's many, many, many different ways of processing the data. So even with PET scanning, there's like a single metric, so it's actual more clinically interpretable. But with fMRI, there's many steps. Each step makes a big difference in terms of how you interpret it, and each one might change the results. So we need to come up with a robust pipeline that everyone agrees upon. And also what's interesting, what sort of is counterintuitive, is that right now we have all kinds of open access programs for analyzing data. Most of what we have is open access. And in order to get a processing method FDA approved, it needs to go through this whole process, which is extremely expensive, and there has to be a motivation to make money off of it. And so it actually has to be almost a private company developing their own very closed software to do this. So which kind of goes against kind of what the research culture is sort of developing. So it's kind of an interesting tension that I'm sure will work itself out. But it would be interesting. There might require some novel innovations. But there's other clinical applications that don't necessarily require this such a plug and play sort of thing. And I actually think one of the most low-hanging fruit clinical applications is to not necessarily look for biomarkers, but map out what we understand to be the networks of the brain. And from the literature, we can understand what areas of networks show are relevant to certain behaviors. And so, or else with a task or whatever. And then apply neuromodulation. So Holly Lisenby here at the NIH is doing neuromodulation. I think that, and Michael Fox is sort of pioneering this method, using not only fMRI, but also looking at white matter tracts and actually tracing the white matter tract relationship to disorders. And the goal here then is to put someone in the scanner, characterize their brain and how it's unique, but then knowing where to modulate based on what's understood from the literature, either enhance or decrease the activation in specific areas using TMS. And to the degree that TMS is effective, it could be very effective in treatment. So here's just examples. It could apply for many different things, everything from Parkinson's disease to Alzheimer's to chronic pain or things like that you might be able to use fMRI to guide TMS. Because right now TMS is just kind of relying on landmarks, and it's kind of a black box right now. So using fMRI to guide TMS, I think, could be an immediate clinical application. So, okay, another challenge. As I mentioned, to develop biomarkers well, we really need to have full individual subject characterization. of similarities and differences. Are we similar? Are we different? And there's been a lot of really outstanding work along these lines. One of the first that sort of helped jumpstart this whole thing is the work by Emily Finn. Before she came to the NIH, she was working with Todd Constable, and she developed this thing called brain fingerprinting, in which you're looking at basically the strength of, and this is using resting state. She's obviously, as we all know, has gone on to doing naturalistic stimuli that kind of drive the brain in certain specific ways. But basically, she found that just a measure, one of the easiest measures to get at people is their intelligence. And to the degree that that's meaningful, they found that there's specific networks that show a difference in correlation that's linearly related to intelligence. And so that's one approach of basically looking at resting state connectivity, finding these networks, finding the networks that are most informative as features, and then simply drawing these comparisons or maybe bootstrapping based on a number of networks. So you can imagine doing this for, she's done this for trait paranoia. You can do this for, things like, levels of depression or clinical symptoms, or you can do it for, other normal ranges of things like, typical ability to, learn video games or some things like that. So, or impulsiveness or ADHD or whatever. So the idea is very basic. And so that's kind of the hope. And the way it kind of goes beyond the Merrick paper in some sense is that, it's sort of you have a continuous measure of something. And that's kind of key. It's not like two populations that are pooled. You're trying to sort of look more closely at the population and parsing one specific variable against the data, which makes it a little bit more powerful in that regard. My guess is that if you just chop this in half and try to look at 2,000 people that are either, above a certain level of intelligence or below, my feeling is that it might not be as powerful as trying to plot a continuous measure. So that challenge is actually, to me, the challenge is to get good behavioral measures. I think obviously the challenge is well, and I asked actually Bug Depley about this a long time ago, but same thing with the Merrick paper. It's still not clear. And one challenge to develop with fMRI is that it's not clear that all these subjects' brains were normalized and parcellated looking at precisely the same area of brain tissue. So a lot of these resting state connectivities could be driven by some specific area of the brain that might be a little bit out of place, that was in the spatial normalization may not have lined up properly. And so that might cause a systematic error. So really a big challenge in properly advancing fMRI along this line is how do you really align different structure and structure-function relationships precisely. Another puzzle to that issue is that maybe it's the misalignment that is a feature as well. So maybe you might align perfectly, but then you get rid of all the salient information that helps you differentiate them. But it might be trivial that it's just something shifted, but that still might be relevant. So it's a challenge. So, all right. So layer fMRI. There have been several talks on layer fMRI. I'm not going to go into it, but I am going to go into sort of what's the big hope of layer fMRI. And the big hope of layer fMRI is that the entire brain is organized into these hierarchical layers that feed forward and feed back. And they feed forward from specific areas in the layer organization. Like they feed into layer 4, and they feed back to upper and lower layers. And the idea is that there's this hierarchy of ever more sophisticated, ever more detailed models of every aspect of how we experience the world. that keep on feeding back to the previous layer down to sensory input. And and you can, understand how the brain makes sense of the world through understanding how these layers are, how these areas are talking to each other. And you know which direction the information is going based on where the activation is. So there was a lot packed into that hope. That it's a lot of assumptions right now. Most are probably, at the very least, highly nuanced and very different than what I said, and some are probably just plain wrong. So we're at the very, very early stages of just getting robust layer activation on a whole brain level. And so we're just starting the very first proof of concept studies that might suggest that this hierarchy holds, but it probably doesn't hold in many other ways. So this is just an example of feed forward dominated column, and then this is sort of the feedback dominated column. That's the basic idea. That's the basic hope that this will really enhance and inform models of the brain. And so we can do this as a whole brain level. There's tricks you can play to reduce the TR, various techniques developed by Renzo and others, and also Yuhui Chai, that can get whole brain blood volume sensitive layer fMRI. And, these are dramatic pictures of whole brain, high sensitivity activation. But one problem that I don't think is mentioned that much, just because people are just trying to make sense of little bits of data. And I think this is a real issue. So one, we have low signal to noise in these data. And two, if it's whole brain, what do we typically do when we analyze whole brain data with low resolution data? We put it in normalized space, we parcelate it, we look at the time series, maybe 200 time series, and we see how they correlate. And then we see the features. You really can't do that very well. There's a couple of problems. One is that at this resolution, the functional organization of the brain, as delicate and fragile as parcellation was at 3 millimeter resolution, it completely falls apart when you try to average across brains, with, for instance, ocular dominance columns. Ocular dominance columns are somewhat quasi-random. So how do you average across subjects, ocular dominance columns? You just can't. It has to be some way, like some sort of mathematical approach, like hyperalignment that Jim Haxby has been developing. So that's one problem. The other problem is that it's just an explosion of data. So in this case, one sort of stab at this data has been to say, okay, let's take the resting state network and let's consider the layers along each blob of activation as an element in this matrix. And then let's see how these layers across these blobs all sort of average together and how they correlate with each other. And you might be able to derive some sort of measure of how these blobs are speaking to each other. Okay, but that's just like, a tiny, tiny, tiny fraction of the data that you collected. So, and you can do that with each one and try to, and you can make a story and you can write a paper about this, but what we really want is some way of looking at the entire brain across layers in a robust yet sensitive way that captures dynamically like all the interactions as they're happening across layers. So we're limited in signal noise, and we're limited in just simply the processing power to do this in any sort of way that's computationally efficient. So that's a big challenge. We have more data than we know how to analyze robustly, in my opinion, at least. So, but it's a fun challenge because it's, obviously it'd be nice to increase the signal noise so we can do more with the data, but once we do, then that'll be a really interesting challenge to sort of look for patterns in a way that's both sensitive and robust. It doesn't miss anything, but then also gets at what's most important. So the next challenge that I want to look at is subcortical activity. So I'm sort of skipping over multimodal integration, but I want to just address a little bit of subcortical activity because it's so relevant to at least NIMH, the mission NIMH is that, so many studies, we can look at the cortex because we can look at the cortex, we've been studying the cortex and trying to identify networks in the cortex that are related to disorders. But all those might ultimately be a secondary effect. Most mental health disorders, I would venture, are probably related to subcortical regulation problems that are ultimately in, the thalamus or other parts of the subcortex. That if we could actually image those with high fidelity, we might be able to get more directly at biomarkers that might relate to specific types of disorders. And I show this because this is a beautiful, beautiful study, one of my favorite studies by Javier, averaging the heck out of the data and showing that whole brain is active. But he also showed that comparing to a atlas derived by using FSL, not FSL, FreeSurfer, he found unique patterns of activation with a finger tap that also seem to follow the structures as they're shown by FreeSurfer. So there's subcortical organization, and if basically looking at that more carefully, you can see the subcortical organization, these very strange time series that one wouldn't, this is kind of normal, but there's other ones that are not what you would expect. So you need sort of a open-ended sort of modeling approach to do this, but getting at subcortical activation robustly is, I think, the next thing that we should be focusing on as far as brain activation with disorders. Oops. And this is I just want to show one example of where one study actually showed a beautiful example of using seeds in the subcortical areas and then showing the correlations as they vary across the entire cortex. And it shows, this, pretty rich tapestry of correlations that seem to show functional organization. So suggesting that the subcortical areas show unique communication in time with different parts of the brain. So it sort of coordinates things. Tying that all together hasn't been done yet. All right. Like I said, temporal and spatial resolution of 10 milliseconds and 0.1 millimeters. We can get one or the other, but we can't get both yet. So there might be a way of getting both in some sort of way that might take a long time, but you get at that resolution. You can certainly do that. Okay, so as long as you have like some sort of well-repeated sort of study, if you can repeat your paradigm identically, then you can easily get at this temporal and spatial resolution. It just takes repeated measures, different TRs relative to what the activation is, and also, high resolution in which you have to collect the data. Okay, more contrast in the same time series. This is kind of near and dear to my heart because I feel like this is something that MR physicists love to play with. And it's something that when fMRI began, it existed a little bit, but not that much. And I feel it's such a wasted opportunity. So right now we do either bold or we do vaso, which is great. Or, we've gone into multi-contrast with multi-echo, and everyone in the neuroscience community is like, oh, this is great. We can collect multi-echo. We get all this free information. But that's just the tip of the iceberg. You really can get, you can combine spin echo and graded echo. And with that different information, you might be able to get measures of vessel size, baseline vessel size. You might be able to get rid of your noise better by saying, well, the noise is different across these three different contrasts, but to the extent that they overlap, that's like truly the artifactual noise or something like that. You might be able to, any sort of multivariate assessment not only increases your signal to noise, but if the information is unique, you might be able to derive unique information. You might be able to leverage more power to interpret the data. You can get simultaneous perfusion blood volume in bold as well to get at metabolic rate, for instance, directly, without a calibration method. If you can get at, you can do it with and without diffusion weighting to remove intravascular signal to see the contribution of that, or to remove the CSF signal to see the contribution of that. Of course, different flip angles modulates inflow, and with and without magnetization transfer, sort of gets at differential tissues that are more or less packed together. So all this information we could collect, almost simultaneously, not all at once, but with some cleverness, we can actually get at different physiologic information to not only better remove noise, but to better interpret the signal and to increase our signal noise. So it's there, it's able to be done, and it sort of highlights the nature of one of the natures of the problem of fMRI in general. And all of these challenges, I think, can be addressable, and they could have been addressable years ago if fMRI were clinically applicable. That way, vendors would care about it, and they would put a lot more man hours into, or people hours into doing this sort of thing, and the progress would be made faster. Right now, this is all sort of in the domain of physicists and people sharing, certain sequences that are research sequences, but it doesn't really make traction with a broader audience because it's not a clinical product, and the vendors don't care until it becomes a clinical product. So it's sort of a chicken and egg problem. So we need to get our foot in the door clinically to get things going. So with all these contrasts too, one of the things that physicists are having fun thinking about, and that is not only getting hemodynamic measures of the hemodynamic transfer function or oxygenation, but also trying to get at other aspects that are related to physiology but are not bold, like the lymphatic system. And the lymphatic system presents a unique challenge because it involves CSF, but it involves CSF kind of flowing right next to the vessels at about the same velocity in the perivascular space as the vessels and the capillaries. And then it goes even slower. It's flowing a little bit faster than diffusion, but maybe in a directed way from across neurons. So how do you actually image that? It seems like it's able to be done if you can become sensitive to this variable flow and leveraging all the information that we know about it. We should be able to get at it. But so far, we have not had a very robust way of getting at the lymphatic system, which could have large clinical consequences because it could be central to a lot of disorders, since disorders of the lymphatic system then lead to or indicate brain inflammation, which might be chronic, not really noticeable in most people, but then lead to disorders down the line, everything from Alzheimer's to psychiatric disorders. Other aspects, I mentioned inflammation as well, but also we have the capability of looking at neuromelanin, which might be a proxy for dopamine function. It seems to be very much the density of neuromelanin is related to how much dopamine is accumulated in the substantia nigra, so that people are just starting to understand how that's, just simply having a high contrast image where you're looking at neuromelanin might be another biomarker. It's definitely something that is related to Parkinson's, but it's also could be related to things that are all related to dopamine function, depression, schizophrenia, whatever. And it might be a target for modulation as well. So with that, one last thing. Uniform shimming across the whole brain. I mentioned that this should have been solved because we have completely the capability of making a uniform magnetic field in all the nooks and crannies of the brain where the brain varies with the scanner. It's just that it's not something that is clinically necessary. and it involves some engineering. So basically, right now, clinical scanners have the shim coils in the bore. And they're configured such that they're orthogonal to each other, and so you can tweak the currents and get things good enough for most clinical scans. You don't even notice bad shim anymore in clinical scans. But obviously, when you go to 7 Tesla and you're going to very high resolution or low resolution where you see signal dropout, you need that solved. And there's been some work along those lines. Most notably, Larry Wald at MGH has been doing this is just one example. People have put passive shims around the head. They've had coils, orthogonal coils at the head. He's developed what's called an AC/DC coil. Basically, it's using the RF coil as a shim coil as well. So passing DC current through the RF coil as well. And it fixes shim pretty well. It gets you close. So I think actually shim is solvable. It's just a matter of how much, at least right now, how much bulky engineering you want to make do with to solve it. And so it's this trade-off between, well, is it that big of a problem? For some, it's worth it. Others, it's not. So anyway, so with that, just to summarize all the previous talk, we went over controversies, practices that may be incorrect, discoveries of shortcomings that get amplified by non-experts. That's the nature of most of the controversies in fMRI. Findings that are intriguing but haven't been widely reproduced, like neural current imaging or things like that. Some of the mysteries. I kind of like collecting the mysteries and things like what's the purpose of resting state? Why is resting state fMRI there? Why is that sort of thing is sort of fun. And now finally we went over all the challenges, not all the challenges, at least the ones I can think of. And I barely scratched the surface of how we've been addressing each of these challenges. But I'm pretty optimistic that all of these are addressable and we can continue to make progress, if not solve them. Of course, there'll be new challenges that come up after these, but I think that they're all doable in terms of solving. So with that, I'd just like to end with more disturbing images and address any questions. Thanks. Any questions? Any questions from from this gallery? I don't even know. I can't even see it. But is there any questions there, Pete?
Yep, no online questions yet.
All right. All right. Well, I'm always, everyone knows how to reach me. So.
Oh. So I was wondering maybe to add to all the challenges, the challenge of integrating communities throughout the world to be able to tackle these challenges.
Yeah.
Because many people might sometimes are thinking or interested in similar things, but it is also a challenge to create the synergy and make them work in an efficient way such that mental resources are not wasted.
Yeah. I sort of mentioned that in some sense. We're right. There's this. I think the challenges will only be done. That's sort of like one of the most effective ways of doing it. It's like having really transparent ways of organizing around the world these groups, because no one group has enough resources to actually. Even MGH or the NIH. There's always benefit from having more people thinking about it. But then the challenge of that is having them all coordinated in such a way that they're all sort of actually making progress and it makes sense. So yeah, I think that there might be creative solutions to that. There might be, people have tried to have like Renzo has his layer working group. That's sort of like a proto group that could actually come together to address things. There's hackathons at OHBM that kind of does this. But yeah, if it could actually be something where you have a clearinghouse of ways that you can collaborate and actually, coordinate the collection of data, the processing, and the development of tools. That would really be cool. I think that would be helpful too. It would help accelerate things. And things are kind of going that way, but it would be, I think it's just waiting to be done. You know, some sort of, you know, website or something that's a clearinghouse of collaboration. So who knows? Maybe we can start that. Right. Well, thanks.